homework, I just want you to be aware, this is not how we would really build this thing in the real world, okay? People would freak out if you tried to build this thing, okay? But
is number one going to be constant?
number one going to be constant.
Step one. Your concrete strength.
Yeah, the
Big
concrete
number one.
weight.
This?
Yes.
Uh,
Not the H, but the
yes.
the strength.
Always assume that we're going to be using normal weight concrete.
Okay.
So
And
150 pounds.
Yep, and from the standpoint of, I've never used a value outside of 150 pounds per cubic foot. Now I can tell you that concretes are gonna come in, now I've tested concrete from all over the country. It's gonna range between 140 and 158
So
pounds per cubic foot. For
If
the
it-
purposes of estimating though, with that variability, 150 is certainly suitable.
so if H was 18 inches, we'd put 1.5 times 150 and then minus that off the soil.
Yes, yes. Yep.
Okay.
Yep, yeah, this worked out really nicely because we used an H of 12.
Yeah, that's why I want to make sure that.
Yep,
All right.
yep, yeah, very good point, yeah. So what Rush was asking is, if we instead used 18 here, what would the pressure of the concrete actually be? 225 pounds per cubic foot, or per square foot, sorry. Okay, so, and the same if we reduced it to 6, then we just half that number, okay? So that's why it's nice to use these easy numbers, 6, 12s, 18s. It's not always gonna work out that that's what you will actually recommend for your design, it just makes the initial calculations easy, okay? The next step that we want to look at, we want to now figure out, okay, so once we know this width, what's our effective depth of our footing?
So that's number 5.
Yep. And I don't know why your book went away from this, chose to at this particular point. But if you're following along in the book, and this is what we'll do for the portion of this class, but be aware that they're missing things in analyzing this dimension. And it should become pretty obvious to us right away. Okay, so it's going to equal our H, right, our effective, where did I put this thing? Remember that our H is our distance from the top of the footing to the bottom of the footing, right? Okay, so what are the things that we have to take into account?
Where's the? We're looking to see how far we sink that underground, or
No,
Oh.
sorry.
oh,
We're interested in figuring out the distance D from the top of the footing to the middle of this really, really poorly represented piece of rebar.
so half the
Right.
bar diameter,
Yep. So you need half the bar diameter.
and what'd you say it was? Was this still 1.5, or would it be?
Oh, no, that's a good point. I did miss that. I did miss that.
You know, well, you gave us 2 examples. You said in columns it always 1.5,
Yep,
and then
yep.
something else.
For footings, if our distance is between a formed face,
3 inches.
we're going to limit it to 2 inches. Okay? If the distance is to an unformed face, we want 3 inches. Okay? And we're just giving ourselves a fudge factor. So what's going to happen to that concrete out here at the edge of this unformed face? What's it interacting with?
So
Soil.
It's interacting with the soil. So there's going to be some moisture migration. We're not going to get as good consolidation at that point. Okay, so we can't rely on getting consistent strength there. Okay, so let's put here. Cover equals 2 inches for formed faces, not fond faces, not fond faces either. Formed faces, and 3 inches for unformed. Okay? What would be something else that we would have to take into account? What were we taking into account when we were looking at beams?
Well, the bar, are we just saying that it's one?
We gotta
bar?
support these things, right? They're just floating out in free space before we pour them. Your book, however, for whatever reason during this section, has removed any sort of support for the rebar, okay? So we have to suspend belief in gravity in performing these calculations, just to be consistent with what you're gonna see in the book. Okay, so this is the equation that you're gonna use. You're gonna use your assumed height, subtract half your bar diameter, and your cover.
Are we going back to 1 inch, or do we actually gotta plug shit in?
I would just continue using 1 inch here.
Okay.
Yep. I'd continue using 1 inch for your bar diameter. Okay, so for this value, what does D end up being?
So 12, 8.5?
Yeah, 8.5.
What's that?
So we're not gonna add a stirrup or a mesh?
So I typically would, absolutely. I would. In this example, I don't know why in this portion of the book they decided to drop that completely out.
Get a bottle
So
throw.
just to be consistent with what they have.
And that's gonna continue for the homework problems?
Yep. Yep. But yes, make sure that you recognize in the real world, rebar doesn't just float in free space, right? Okay. So the next item that we want to look at then is, so now we figured out what this effective depth needs to be. Okay, so now we can figure out what type of pressure is this soil going to exert back on the footing itself, right? Because remember that every force has an equal and opposite reaction. Okay, so our soil is going to push back on that footing. Now, because the footing is a structural element, okay, this portion we do have to use a factored load. Okay, and remember that that's the 1.2 dead load plus the 1.6 live load. We still don't have to take into account a rough load here, right? Because we're dealing with the footing. First. Yep, 12,500 pounds per foot. Okay, what's up, man?
Where do you want your beam tester?
Ooh, wherever.
Actually,
No, we're not gonna have time to run them today. Yeah, you just bring it in here. I'll start breaking it down in between classes here.
Such mysterious packaging.
Okay, once we know.
Not gonna tip your delivery man?
Is that?
You're not gonna tip the delivery man?
Yeah. How long it takes that long to get the thing? We can now figure out the percentage of that pressure that's going to be applied on the area of the concrete itself.
what does D
okay?
stand for?
That's so dead.
That's what we just figured out.
That's,
That's
That's the
8.5
depth, right?
inches.
yep.
Okay. I'm still
Due-
making sure I
Yep.
identify what
Yep.
D I'm talking about.
Due to the effective depth.
figured out right there.
What's that? WU is your ultimate load due to the soil pressure, okay? And it's a factored load, okay? And so you're going to divide that by the thickness, okay? And that thickness is going to be, typically you'd have to multiply it by a soil correction factor. They haven't told us what our soil correction factor is. They're using a value of 1. Okay.
6 inches.
Thickness is
6 inches?
Or sorry, this thickness is not correct.
Killing me.
son of a gun.
Width, sorry.
Do we stick with a 4 point?
What were you gonna ask, Rush?
I was making sure that you didn't.
Yeah,
go
I'm
up to
just,
5
yep,
or,
yep.
you know
No,
what I
I'm
mean?
just using
So
4.75.
then it goes down to pounds.
Oh, shit.
Okay?
That's pound feet. Oh yeah. So
The next thing we want to look at is we need to figure out our critical sections for shear and bending on this footing. And so we got to think in the abstract for a little bit. Okay, and once we talk about it abstractly, then we'll figure out what the actual dimensions are.
It's all in the abstract for me.
What's going to happen to this column when we think about just the pressure from the soil itself? What is the pressure going to try and do to this column? Or to the footing, sorry.
Rotate it up.
Rotate it down.
It's, okay, yes, it certainly will have an element where it's going to want to try and bend it, right? But isn't it also going to try and be shearing it? Because remember that you're going to have the load of the building being transmitted through this wall.
Oh, yeah.
So it's going to do both, right? It is going to try and rotate your footing up into the wall, but it is also going to try and shear that footing off as well, okay? So we need to figure out what the critical dimensions are for shear and what the critical dimensions are for bending. Critical dimensions for bending is very easy. That's your critical dimension for bending. The face of the concrete, or sorry, excuse me, the face of the footing to the face of the wall.
So would we take 4.75 minus 6 divided by 2? It's a 6 inch thick wall, right?
If you're going to do that, convert your 6 to 1/2, right?
Yeah.
Because you got, yeah, I
'cause
agree
we're in
with
decimal,
you.
we're in a decimal foot, but.
Yep, exactly. Yep, that's all that you need to do. Yep. Yeah, so what Rush said is, he knows
125.
that's 4.75 feet.
Mm-hmm.
He knows this is 0.5 feet. So he wants to take 4.75 minus the 1/2, divide it by 2. So he's subtracting that portion out, right? And that's exactly what you're left with. Okay?
So smart.
That ends up being, what's our critical section here for?
2.1.
2.125.
Write that stupid thing.
That's number 8 then.
Section for shear.
Yeah, you need to write step 8 down, so okay.
What's that? Oh, sorry. Yes.
Parker ran off.
I'm being a sarcastic.
Critical, what was it? Section?
Critical sections. For shear and bending.
So that would be W minus T.
Okay?
So what was the formula?
So bending is just distance from footing face to wall face. Right? And maybe it helps. Grown so accustomed to only having one color of marker.
What was? I thought that was shear.
Shear and bending.
Nope, this is just bending.
Oh,
Wait, so what Rush suggested or what he said was only for shear?
that's, no, for bending.
For bending,
That was only for bending.
for bending.
So now we have to do something separate for shear?
Yep. No, this is still step 8. It says right here,
8.5.
critical sections for shear and bending. Shear and bending. They can be different values.
I don't even know.
I still don't
anymore.
know.
So do you take,
I want this.
since it'd be evenly distributed, right?
Our critical value, our critical section for shear, we're going to take, it's not another D, it's the same D. Same D,
Okay.
dimensionally speaking.
Okay.
We're taking that distance that represents the top of the footing to the middle of our steel, right?
Yeah.
Setting that against the face of the wall, okay? However far it projects, our critical section for shear is the distance from the footing face okay? Distance from the footing face to the projection of that effective depth from our wall face. Okay?
So basically, D minus, or your bending
Like 2.12.
length minus D, wait,
Bending
but
length.
D, yeah, because
Yeah,
Can you
Absolutely.
just
You gotta
write it out how
convert-
you'd solve it, like
you gotta
mathematically
convert
instead of writing
D
the words?
into decimal feet.
Yeah.
I got 1.425 feet.
I just want to see how you
Yep.
solve it. So, because that'd make more sense than. I don't know.
so we'll call
No, I hear
this,
I hear you. 'Cause I will not remember how I figured it
No, I'm mad. That's what I was trying to.
Bending section minus.
out. 1.425.
Okay.
What'd you get?
this
How'd
is
you-
your bending.
Oh,
right?
Yeah, I rounded.
Your total width divided by your thickness minus 2.
Okay, thank you.
Okay?
I did. Yeah.
Convert D
Okay?
to decimal feet. We said it 2 classes.
Okay, now we can go to number 9.
Oh, yes.
I think we'll have to end here.
Yes, you got me close.
So, the first thing that we need to figure out, we need to figure out our ultimate shear value. Okay?
Ultimate shear.
Yep, our ultimate shear value. And what we're going to use is that maximum soil pressure, right? Because that maximum soil pressure is what's going to apply the maximum shear value, right? Right? Everybody's nodding their head yes? It hasn't been that long since we did work on shear, right? That we remember that that's what that means?
Memory dump.
I was about to
Yeah.
say,
Got it. Where'd you get the 26?
Number
2630, so here we took our ultimate weight
Yeah.
and had multiplied it by the width to get it back into a form where it's being applied across
Okay.
the strip footing. Yep.
630. I don't know where 16.9 came from.
Remember that we said that this equaled
2.125.
Oh, does that come from 8?
Oh, you're converting into inches. I was doing decimal feet.
You could do that too. It'd be the same thing, right? Because what does this end up being? 2.1 feet or something?
Yeah.
Yeah.
For the equation on number 9, can you just write out like what you're multiplying? Because I think a lot of us are kind of confused when we're pulling
Yeah,
this.
I'm still confused
So
with
it's
16.9.
it's max soil pressure
Oh.
times, you know what I mean?
Label what these
Right.
values
Yeah.
equal.
Yeah.
Yep.
Thank you.
You ended that beautifully.
Okay, and then this is our critical shear. And then this is just gonna be a conversion. Okay, because this is in pounds per feet squared, and this I have in inches, okay? And so, yeah, let me finish this here. And I think once we plug that in, we'll be done. Let's see, this is black.
You have 3-hour class, you over one problem.
Oftentimes. What did we say D was, 8.5 inches?
Screw engineering.
Okay. And then, so our conversion is, let's see. 1 foot. For 12 inches. Okay? So our ultimate shear ends up being 3,700 pounds. Okay, so we'll wrap up here, we'll pick up with our analysis there, we just
So
have
how
a
come you
handful of
just
steps
didn't
left.
use the 6 or 17 inches instead of 16.9? That's the shear.
I'm still trying to figure out where it's, how did you get 16.9?
Isn't that from the shear down there?
Yes,
So why'd you use 16.9 instead of 17 inches?
I think I must have did different rounding when I did that previously.
You just go on the sheet that he previewed up.
Yeah.
Oh, okay.
I mean, if you plug in 17 here.
No, I was just, because that's big, that's where you got it from though,
Yep.
right?
Yeah,
Okay.
yeah.
That's just all I'm trying to win.
Yep, this is.
Yeah.
Yeah. Yeah.
Got,
I'll be looking at that for the video.
Good thing I'm an engineer in my house.
we'll test the beams on Thursday then, since this thing is here.
Oh, we gotta put that together. Then,
No, it's, if you're pulling out the stuff, the compression setup.
oh,
plugging
it's
that
the
thing
thing
in.
for that.
Yep.
We get to break shit.
Yep,
Now we're
get to
talking.
break those beams.
Mind is fried.
Of course.
Where's